All right. In this example one here, we're going to try to go through and verify each of the three theorems. So uh, hopefully this will make sense as I go through each piece and try to explain the overall parts together. So the first theorem is referring to the eigenvalue and eigen. It says that the transition matrix of the Markov chain with lambda equal to 1 is an eigenvalue of t if x is the eigenvector corresponding to lambda equals 1 with non-negative components, then 1 over s times the eigenvector x is an equilibrium vector. So here's the matrix T corresponding to our system for the different meets and whatnots and so on and so forth. And so we're going to then choose our eigen values from T. We get 1 is definitely one of them. Negative 1/5 is a repeated as well for this particular eigen matrix, or this particular matrix, transition matrix T. And so the corresponding eigenvector is here. This is the first one, 1, 1, and 2. So if you add up the components, that's this S down here, that is equal to 4. So 1 plus 1 plus 2 is 4. And so the equilibrium matrix is 1 over S times the matrix. And so we should expect that as the number of iterations goes to infinity, that way it should balance out to be 0.25, 0.25, and 0.5. Okay, so those are the equilibrium conditions we're expecting to see. So this is theorem 1. And if we verify that, that's a simple thing to do. So in this first example here, I'm making the choice that he's going to choose liver for the first one. So x1 here is if his first choice on day 1 was liver. And so plugging that in, you get m1 times x1, and that gives us these values. And so imagining as time goes on here, you can see down here in M2, you get the same value. So he's choosing his choice here for the first day, or first meal or whatever, is liver. And then as we move across the number of meals, you can see they're converging very quickly. So in fact, n equals 1, you get 0.3, 0.1, and 0.6. So it's not quite there, but after n equals 2, so just after 2 iterations, it's pretty close already. And then if we move to n equals 3, it's almost identical, 0.25, 0.24, and 0.5 to the equilibrium of 1 over s times the eigenvector associated with lambda equals 1. And as we continue on, then it definitely flattens out. So even by the 5th iteration, we're there. In fact, by the 4th iteration, we're actually there for the case when we choose liver. We can also choose, what if it wasn't liver that we wanted, but ribs? Okay, so this first one is the case he chose ribs. This X2 is the case where he chooses ribs. You can see down here, what does his long-term behavior become? So there's the first iteration, the second iteration. So already at the second iteration, similarly, we're pretty close to the steady state expectations. And so in that case, if it chooses liver, it's definitely within 3 iterations. So it's actually one step faster than the choice of liver for the first one. If it chooses ribs, it converges in 3 steps to the expected value of the long-term behavior. Right. So theorem 2 says that the transition matrix from the Markov chain, kind of like what happens when t approaches infinity, that's the number of iterations, it should approach a matrix L whose columns are identically equal to the same vector x. This vector x is the equilibrium position. So let's go ahead and calculate or look at that example next. In this example, this is the iteration. So what it's saying in the second theorem is that as n increases, or as k in the actual theorem increases over time, right? If you get multiple iterations of it, you should see that each of the columns corresponds to the same eigenvalue and eigenvector of 1 over s times 1, 1, and 2. So this eigenvector over here. So if we continue to increase the number of iterations, so here's n equals 2, n equals 3, n equals 4, you can see that it's quickly, so after even 4 iterations, it's almost there at 3 iterations when n is equal to 3. N is equal to 3 here. The only term that is not there is this A11 term. But if we go to n equals 4, you can see that each one of the columns for this iteration matrix or this transition matrix approaches the 0.25, 0.25, and 0.5 of the eigenvector associated from the first theorem as expected. Right? And then in uh, the third theorem was talking about let T be the transition matrix in the Markov chain with steady state probability vector x. Then for any initial probability vector x naught, the sequence iterates xk approaches x. So no matter what value you choose, you should approach the transition matrix. And so we've already kind of seen that. We chose x2 here, which was the choice for, is it liver? Or no, ribs. And then we chose for the case when it was liver. So the only thing we haven't chose or looked at is when x3 equals, should maybe done those in different order. What happens if we choose fish for the first meal? And boy, I don't know why that seems difficult to input at the moment. Okay, so we do t to the n times x3. Okay, so it definitely does. If we come back, it's s. Let me move this back to where it should be at 4. Okay, and move in along. Okay, so there it's verifying that this is the case when we were choosing fish on the first day. Let's move in to 1, and there's a probability for the first day. And then go to the next one. Okay, it's getting closer. It's a little further off than previous versions, but n equals 3. N equals 3, it's about the same as it was for the ribs case. And then by 4, probably is going to be exactly, yeah, matches exactly. So for no matter which choice we choose, x1, x2, x3, in other words, if we choose fish, liver, or ribs, theorem 3, we just verified that theorem 3 does come true, that no matter which initial conditions we start with, it does, after at least 3 iterations, certainly 4 gets it each time to the theorem 1 result, which was 1 over s times the eigenvector associated with the eigenvalue of 1. All right. Hopefully that made more sense than it was complicated, but hopefully you'll see the connections between the 3 theorems and how the iterations play off with the corresponding eigenvalue of 1 and eigenvector towards the long-term behavior of the Markov chain. I hope that was helpful, and I will see you in the next video.